Okay, so I'll go ahead and kick off. So my name is Julian Chesterfield. For those of you who haven't met me, so I'm Chief Scientific Officer at OnApp. Prior to that, I was formerly part of the XenSource team. I did my PhD at Cambridge, so I've been involved in Zen for a number of years. And kind of coming back to it now through some of the work that we're doing at OnApp. And I'm here with some of my team as well, who are joining me as a bunch of guys who are working on some of the lower level details of what we're implementing here. In particular, we've been revisiting some of the architectural assumptions around how we deploy Zen, virtualization, multi-tenancy support on top of low power MicroServer ARM-based devices. And I'll also talk a little bit about some of the interesting challenges and design challenges that we have around integrating FPGA I/O acceleration as well. So just a little bit of background, setting the scene. I think everyone here is familiar that there's a lot of focus on embedded and integrated system-on-chip hardware. The mobile device space is booming, of course. Autonomous vehicles, there's a lot of custom hardware design that's happening in that space. We're also particularly interested in the edge server case, so having smart devices close to the edge that can handle multi-tenant applications and services. And this is kind of the primary area that we're focusing. We're also, very interested in the sort of autonomous vehicle space as well. So in pretty much all these cases, ARM features very prominently in this landscape because of the power efficiency to performance ratio, and also the sort of open ecosystem around ARM. So there's a lot of vendors that are involved in this space, and there's a lot of custom design going on. One of the challenges, though, of course, is that these devices typically have much lower resources. So in the sort of Intel server data center case, we've become very used to having lots and lots of RAM, lots of CPU cores, fast I/O interfaces, and so on. Of course, in the embedded device case, we have to be a lot more conservative in that regard. So particularly with the devices that we're working with, which is based on the Samsung Exynos processors, the ones that are used in the Galaxy S6 phones. The current generation of processors only have up to 4 gigs of addressable RAM per cache coherent node. So this is quite a significant limitation. So in parallel to this, of course, the other thing to point out is that there's a lot of interest and there's a lot of growth in the sort of integrated accelerator space as well. So we're starting to see a lot of emerging co-processors, both in the sort of ARM Xilinx case with the Zinc processors, the UltraScale Plus devices, but also, of course, with the Intel acquisition of Altera. It's no secret that they're bringing out a co-processor that's going to have embedded FPGA acceleration as part of that. So at OnApp, our core business is in cloud orchestration. That's something that we've been doing for a number of years. We're quite established in that space. We're about a 6-year-old company, a little bit past the startup phase now. So we focus a lot around hyper-converged infrastructure, particularly for public cloud services. And we're particularly interested in, we have our own software-defined storage technology, and we work closely with everything software-defined today in the data center. The way that I kind of position this is that making everything software-defined is great because it gives you a lot of flexibility. You can move all this stuff into software logic. You're no longer dependent on very specific hardware appliances in the infrastructure. But the challenge, of course, is that a lot of these technologies have significantly lost performance during that process. So one of the things that we're really focusing on is trying to bridge the gap, particularly with the emerging hardware acceleration capability that's coming into integrated processors. So we're looking at ways to offload a lot of the the software-defined capability actually into FPGA or GPU hardware. So we're working closely with a partner called Kaleo. So this is a startup that's based in Cambridge, actually in the same building as us. And these guys are it's a group of people, one of whom is also associated with the ARM company, and they've set up a startup and they're developing their own custom integrated server PCB boards, and essentially targeting a very dense compute infrastructure for rack scale computing in the data center. And the board that they produce is very interesting. So it's essentially 4 Exynos processors embedded on the board. These are not, they don't share any resources amongst themselves. They're actually cache coherent nodes, and they're fully remote controllable. And they're attached to some centralized I/O resources, which are managed and controlled by these FPGA units that are also embedded on the board. So there's 2 Xen processors that are embedded here, one of which controls, I'll show you this diagram here. So essentially on the left, we've got the 4 Exynos processors. On the right, you can see the centralized I/O resources. So one of the FPGAs is responsible for driving I/O traffic and controlling the physical 10 gig, the dual 10 gig outgoing ports. The other FPGA is responsible for controlling the direct attached NVMe flash storage. And one of the things that we're focusing on in particular here is essentially pushing all of that software-defined logic onto the Xen processors. So part of the work that we're doing here, I'm not going to go into a lot of detail in this talk, part of the work that we're doing is actually building a full software-defined distributed storage technology that's actually implemented all in the fast data path in the FPGAs themselves. Just to give you some flavor of the system itself, each of these boards that I've shown here is called a compute node, and it has, as I mentioned, 4 Exynos processors. So this one here with the 2 Xencs. There are 4 of these compute nodes per blade, and then within a 3U chassis, there's up to 12 blades. So it's quite, it's an extremely dense compute platform. We're looking at, 1,500 cores per chassis, per 3U chassis, and of course that scales up proportionally per rack. So, some of the challenges here, just at the orchestration level, are, how do we manage and control that sort of scale of infrastructure? And in particular, how can we, at a multi-tenant level, how can we actually really get the best performance and scale out of the system? So just to bring in a new phrase here, this is a term, we're not the first people to use this, essentially software-defined hardware. So the idea here is that you've got software-defined control, so we actually run a full, on the embedded A9 cores on the Xen processors here, we run a full control stack that is a Linux host that can actually run and communicate with other nodes in the infrastructure, and it can dynamically control the programmable logic in the FPGA to set up virtual devices and map those to the virtualization nodes that are running on these processors. So essentially, we've moved a lot of the virtual I/O logic out onto the hardware devices themselves, which means that we can actually strip down a lot of what's happening on the virtualization side, which is kind of the main part of the talk here. So this is actually, this isn't the only design that's kind of moving in this space. I would argue that there's actually quite a lot of hardware that's starting to move in this direction, where essentially you've got a bunch of independent coherent nodes. We're seeing this particularly in the Intel data center case as well. So Intel is moving much more towards embedded, Xeon D style processors, rather than scaling out, more and more larger NUMA systems where. And I think it's fairly well publicized now that scaling up the number of cache coherent addressable cores is not really resulting in the same sort of scale in performance. So what we're seeing is more of an emerging architecture where we've got centralized hardware control for I/O resources that is mapped and shared across these cache coherent processor nodes. The Facebook Yosemite architecture is a good example of this. And you know, I would argue also that, you know, the direction that people are heading, including ourselves, with this sort of NVMe addressable storage over fabric is a similar sort of concept. So multi-tenancy on low power ARM, I mean, obviously, you know, one of the arguments you can make is that, you know, well, now you've got a lot more cores, do you really need a hypervisor in this space, or are you actually better off just mapping physical cores to processors and applications directly? We believe that virtualization still has a very important place on ARM, and you know, multi-tenancy is particularly important, primarily for efficient utilization of hardware, so being able to control and sort of map the resources efficiently, but also, you know, to be able to provide you know, efficient isolation and you know, high availability of services running on top of the systems as well. So you know, we believe that, you know, actually, you know, the ARM CPU architecture is very well suited to Xen. You know, it's very efficiently designed. That the performance of you know, running the Type 1 hypervisor in EL2 on ARM is extremely you know, it's extremely efficient, and you know, there's been various work published in this space to show that you know, actually you know, Xen can actually outperform KVM quite significantly in this space. But one of the things that we see is that a lot of this performance gain is really lost in the Xen architecture by handling I/O. So primarily the I/O context switch into the separate domain, the I/O domain running in DOM0 or in a stub domain is really where a lot of the performance is lost. There's been some, there's a paper by Christopher Dahl that I'd encourage everyone to read and take a look at, where they've done a lot of micro benchmarks on the performance comparisons between Xen and KVM, between ARM and x86 as well, and you know, there's some good indications that, you know, there's a lot of advantages that can be achieved here. But you know, particularly the I/O latency, the I/O performance overhead is where a lot of the performance is lost. So, in light of this, and you know, also the type of design that we're building, where we've got, you know, these sort of integrated microserver systems with you know, very low resources, we started to revisit some of the I/O architectural assumptions around you know, multi-tenant virtualization on ARM devices. This is the sort of traditional, you know, Xen architecture today. Familiar to everyone here. I don't really need to go into details here. So essentially, what we looked at doing was making a few, you know, experimenting with a few changes to see what sort of performance benefits we can achieve. And you know, for the Xen purists out there, you should probably sort of close your ears at this point, because you know, this is where we start to break some of the golden rules around, you know, how you know, Xen architecture works. But essentially, we felt that there was a lot of value in actually moving some of the common para-virtualized backend support into the VMM layer itself. So we started to experiment with building a unified I/O backend in the EL2 virtualization layer that would combine both netback packet switching capability, as well as virtual block request handling as well. So we came up with an architecture where we're essentially terminating you know, block back and netback communication rings in EL2, and we have some very lightweight switching logic that allows us to convert block requests into Ethernet frames and vice versa, and we can then transmit those directly over the network or to another domain with very low overhead. We're using a protocol called ATA over Ethernet for this, which is, it's a protocol that hasn't achieved, widespread acceptance, but it's actually extremely well suited to this because it operates at the raw Ethernet level. The actual packet overhead of including a block request with a very small amount of data that essentially identifies a packet as being of type read or type write or a particular type of command operation is just a very small overhead that goes on the front, and it allows you to specify a virtual LUN that particular payload corresponds to. So we've done quite a lot of experimentation also with packet or with Ethernet frame forwarding in this architecture. So we started out by experimenting with a very lightweight mini-OS-based real-time service driver domain. So essentially moving the hardware driver support into a mini-OS framework that's actually directly controlling the Ethernet devices and being able to forward packets from the EL2 layer via an external service domain. And we also experimented particularly for the architecture that I've just presented here, because essentially we understand the hardware architecture completely, and we're also writing the device drivers for the FPGA control nodes ourselves. So we've also experimented with actually integrating the packet forwarding, the actual hardware control interfaces directly into the Xen layer itself. As part of this, we also had to move some of the Xen bus and XenStore framework into Xen. And this has actually resulted in some quite significant speed ups. I'll present some results in just a second. There's actually, it actually helps to, I think there's been quite a bit of work, particularly from the NEC folks around analyzing some of the setup and initialization delays and latencies associated with controlling Xen bus and XenStore communication in DOM0. So we certainly benefit there. And as part of this, we also had to be able to integrate a management interface that will allow us to remotely control these nodes. So essentially what we're moving towards is what we call a sort of clustered hypervisor model, where there's no control domain that actually runs as part of this hypervisor instance, and we actually sort of centralize all of the management of these remote Xen nodes. And it results in a much simplified sort of image that we can boot and deploy on a system. There's actually no external distro dependency in here at all, so we're not booting and installing a control domain stack. And in our architecture, the reason that we believe this is sufficiently secure, I mean, obviously there's a trade-off here, but in our architecture we have a dedicated management interface that allows us to, we know that, exactly where the control interfaces come from, so we can isolate control from the actual data path and runtime processing of Ethernet frames and block data and so on. Taking the picture a bit further, we're offloading all of the virtualization of devices. So we have the ability on the FPGA itself to be able to map virtual devices as LUNs, which are mapped over the embedded PCI fabric and presented, over Ethernet, using our embedded ATA over Ethernet handling framework. And the same for the virtual networking as well. We can create virtual network devices. It's essentially virtual functions, equivalent to SRIOV, for example. And with the intention, we haven't implemented this yet, but with the intention of being able to offload a lot of the sort of SDN capability for creating virtual overlay networks and so on can all be implemented in the FPGA. This is all managed via OpenStack. So we've got, we've built our own kind of management tools. We have something called Vertex D, which is this centralized component. It's a very lightweight management daemon, and it's designed from the ground up to be scalable. So we can create these sort of control aggregation points when we have this massive sort of rack scale architecture where we can have multiple of these units that sort of aggregate control on a localized basis. So if you think you could have one of these per chassis, for example, and then you can scale that up to a centralized OpenStack. OpenStack, of course, doesn't scale particularly well, but we kind of remove all of that, and we hide a lot of that underneath it. As part of this, it's being productized, so we've built our own management UI with the ability to sort of scale and manage data center scale infrastructure. So there's a number of challenges in here which are kind of independent of the actual hypervisor side piece itself. One of the particular use cases, and also part of the reason that this is a project that's being run as part of an EU-funded research grant that's called Superfluidity. One of the use cases here, and this is particularly why we've focused a lot on network performance, is network function virtualization, particularly at the edge. So we see this as a use case that's gaining a lot of traction, and it's going to be, it's becoming much more common. So the idea is that you can have these sort of edge servers that are close to mobile devices, you can push out a lot of functionality close to end users. And of course, being able to create virtualized network functions in a very lightweight way, so being able to rapidly instantiate these, so boot time is particularly important. Being able to instantiate them on demand in a very quick way, but also being able to do lightweight packet processing in software, but essentially with hardware pass-through, or at least close to native hardware performance for virtualized network interfaces in the network functions themselves. So typical examples are firewalling, NAT gateways close to the edge, custom traffic shaping, so for different levels of service quality and so on, and of course having the embedded FPGA lets us offload a lot of this processing. We've built, as part of our management framework, we've built a management UI also that allows us to sort of dynamically instantiate this sort of network function infrastructure as well, which is sort of a particularly interesting project in itself. So just getting on some of the performance results. So I mean, of course, the first thing to draw attention to really is the actual resource overhead. What we've tried to do here is just illustrate really, these were some measurements that we took recently. This is sort of a minimum domain zero setup in a traditional Xen model where we've got a control domain running with the Xen hypervisor as well, consuming a certain amount of memory. The microvisor code is essentially equivalent to Xen. Obviously there's more functionality in there, but we've also been able to optimize some of the code as part of that. So it's essentially equivalent to Xen. So the first gain here really is that on one of these extremely resource-constrained devices, we're essentially not consuming any more overhead than the actual stock Xen would consume without the control domain. Boot time is the next thing. So by moving a lot of the setup and initialization into the Type 1 hypervisor itself, we can significantly speed up the time that it takes to instantiate paravirtual devices. We've got a breakdown here of where some of that time is spent. I suspect there's no surprises really here to this community. But essentially the boot time for the VM itself is pretty much the same. I mean, nothing really changes there. Obviously, there's some speed up associated with device access. So VMs do boot a little bit faster. But the primary time is really spent, particularly as the number of VMs scales up, in instantiating the framework, the communication latency around the Xen bus and XenStore communication associated with initializing devices. So embedding this in the Type 1 layer has achieved a significant performance benefit. At the performance level, so this is showing the communication latency here between two guests running on the same cache coherent node, so it's on the same hypervisor. And we've done a comparison here. This is on ARM, so this is on an Xgen board. We've done some comparison here between 2 guests running on a stock Xen installation relative to the closest thing we could come up with was essentially using I think we had a SolarFlare card on the same hardware. We were able to match virtual function devices directly, PCI pass-through directly to guests, and essentially measure the performance of the hardware forwarding latency for a guest to a guest versus the red line here, which is the software version running on our microvisor. So of course the performance overhead of transferring context switching between 2 guests, there's no control domain overhead associated here, and so we're essentially achieving close to bare metal performance. This is Intermode communication, so this is actually going via a physical network path to another node. And we can see here there's a number of results. Sorry, the text is a little bit small, but essentially we've got bare metal Linux support on the left, Xen domain 0 measurement here. This is actually on an Intel. This isn't actually on ARM. I think we'd taken these measurements earlier, yeah. So this is a communication latency latency of essentially handling hardware interrupts through the event channel to domain 0, which shows this measurement here. And then this is the latency of actually virtualizing the network performance in a guest on top of that. Here we can see this is a measurement that we took actually at the microvisor level, so this is actually at the type 1 level. We can see that we're essentially equivalent to bare metal performance at the lowest level, which isn't really surprising. I mean, obviously we're directly controlling the hardware at this level. And then this is the overhead associated with a paravirtualized network interface running in a guest on our version of Xen, which we can see is essentially equivalent to domain 0. Some more benchmarks here. This is a unikernel measurement that we took based on this is on rump kernel, so we've normalized this here against the stock Xen implementation of running Redis not as a unikernel but as a standard VM based on Linux, and then we can see the speed up associated with then embedding that as a unikernel and running that on top of stock Xen. And then the performance speed up we see here, which is close to 50% performance improvement. This is primarily for the network-based operations. There's obviously a lot of speed up that we can achieve on packet processing for a Redis stress benchmark. So we think there's a lot of performance benefit here. Summary and status. So just to summarize what I've been saying, that integrated low-power system-on-chip designs are becoming much more common, and there's obviously these are typically much more resource-constrained than hardware that we're familiar with using for stock virtualization. Integrated hardware acceleration technology is also becoming much more common. And it's important to be able to leverage the capability of the integrated hardware. We feel that Xen is particularly well suited to the ARM architecture for multi-tenancy. In particular, we're focusing on network function virtualization for ARM edge devices and also for data center integrated system designs. We think that there's a lot of benefit in moving some of these core, particularly where the hardware is really well understood. We think there's a lot of benefit in moving some of these services into the virtualization layer itself, particularly the PV backend drivers, the integrated block and Ethernet, the paravirtualized block and network frame handling. and also the setup and initialization services. The current status from our point of view is, we have a functional platform with all of this stuff integrated. We have a lightweight remote management interface that allows us to manage and control all of these remote nodes from a centralized point in a very lightweight way. We've also done, we're still working on integrating a lot of our acceleration logic, but we've proved that this is doable and that the benefits are significant. We've also done a proof of concept implementation for some network device drivers on Intel. So we targeted the Intel IXGBE driver, and we've looked at a few others as well. And we're planning to push all of this back into the community. It hasn't really been in a position where we can actually share the code before now, because it's been very much investigation code. We've been trying various things, but the intention is to push this back into the Xen project. So for anyone who's interested in participating and contributing, then that would be fantastic. And thank you very much. Just to say, this is also sponsored work as part of an EU research grant.
Questions?
Okay. Thank you very much for the presentation.
Sure.
I wanted to go back quickly on the context switch things that you mentioned from Christopher Dahl. So I've read the paper also. I disagree on your conclusions here. I agree that there is a performance hit, but it's not because of context switch. In the case of Christopher Dahl presentation, everything is pinned, so it can't be context switch. The problem here is we haven't yet optimized the context switching Xen for ARM, and we, by mistakes, context switch on the idle vCPU. So we save and restore sometimes registers when it's not necessary, and change the override. So I do believe we can potentially achieve very similar number as microvisor in this case.
Okay.
So I was wondering whether you look at that and how did you conclude it was, I mean, the project has been started as we haven't really focused yet on optimization. We've mostly focused on the architecture. So there probably is some optimization to do there.
Okay.
And have you looked at it before?
So, so you guys would know this better than us, of course. I mean, I think that we've started this from the viewpoint of that there are a number of factors that have kind of driven us towards this approach. I think the performance was an important aspect. We haven't conducted these micro benchmarks ourselves, so I can't really talk authoritatively on that. But we do see the same, exactly the same sort of performance on Intel, the same sort of performance benefits on the Intel architecture as well.
So I will not compare x86 on ARM for Xen, not at all. It's completely different ports, very different.
Yep.
We can't say that the benchmark if they are better on ARM, they may not be better on x86 and vice versa. So you need to do the benchmark on both to be sure that it's going to improve.
I think, so what I would say is that the approach we've taken is sort of a fairly aggressive approach, right? But essentially we're approaching it from the viewpoint of we're not going to get much better performance than actually handling the hardware I/O interfaces directly in
I do agree with that. It's a trade-off between security and performance.
So we're kind of taking more of a seatbelts off approach. I think, the motivation here is that, I think it's trusted code from our point of view. And, my viewpoint is that the trade-off is worthwhile in this case because of the performance benefits and the resource savings that we can achieve. I think this perhaps doesn't apply more generally to, cloud data center operation. Perhaps it does, I don't know, but I think that in a more general context, I can see that there are strong arguments against going this way, for security reasons. But then, the reality today is that, we always said that, we could run, driver domains as stub domains, we could move all of this logic out. Reality is nobody's doing that today, as far as I'm aware. So we always have this dependency today where, you know, if there's any sort of, you know, security issue that allows, you know, as a guest to gain access control to the control domain, essentially it's game over, right? I mean, it doesn't matter whether the code's running in the hypervisor or whether it's running in the control domain. I think at that stage you've pretty much lost the battle. So our approach is that, you know, actually, you know, given that it's trusted code, yeah, I mean, the vulnerability there really is at the paravirtual device interface level, but we see that as a valid trade-off.
Okay, thank you. I'm looking forward for the code on the main list.
Yeah.
So I think that I agree with you, by the way. But so another way, in fact, to get, I think, much better numbers will be with the project that Joao and the other people from Oracle are working on, which you might have seen, right? Which assume that DOM0 can actually map the MFNs as a guest. And that way you could, you know, get back a lot of the networking performance that you lose today with net from net back.
Yep.
But however, it wouldn't help with the boot up times that obviously are far better with that model, right?
Yep.
Yeah, and another question. It wasn't super clear to me exactly what you were doing in, you know, in EL2 in the end, but
Okay.
If you have the FPGAs able to access the same memory space,
Okay.
like on the
You mean in this design? Well, no. So actually, in the current design, it's a discrete FPGA unit. So it sits at the other end of the PCIe controller.
Okay, but if it could, you could actually terminate the PV protocols in FPGA logic.
Absolutely, right? and that we kind of that's sort of, you know, the next stage, I think.
Right.
We're kind of focusing on getting this working first, but I think once the integrated, you know, co-processors become more widely available, I think it's a super interesting path to go. Yeah.
So I have one question for the hardware that you chose.
Sure.
Because it was, I'm not sure that some kind of smartphone chip is a good fit for a server-like environment, especially if this is big little. Was it just because it was kind of available and cheap, or Samsung
it's
has it on
primarily
stock?
cost, I think, is the primary motivation. Now, the hardware design decisions weren't actually ours, so we're not actually manufacturing the hardware. But yeah, I mean, I think the focus for this hardware design really was on density. So it's cost and density is the primary motivation. And, you know, of course, you know, these, and I think this architecture will evolve as well. You know, I know that there's a lot of interesting stuff going on in the sort of embedded, you know, UltraScale Plus is a good example where, you know, the processors are emerging that are going to have these embedded cores in them as well. So I think this architecture will evolve. But as of today, this is a system that is going to be coming to market soon, and it's based on, you know, fairly low-cost components using, you know, off-the-shelf, you know, the Samsung processors are extremely well understood, they're well tested. So from that point of view, it's you perhaps know more about it than I do, but I guess the point is that there's billions of devices out there that are using these processors. So I think there's a lot of value from a hardware design point of view, particularly for a startup company being able to leverage that.
Just a follow-up question on the PV terminated at the programmable logic.
Yeah.
So do you think there's any space for perhaps an open source implementation of the PV protocols in
the
RTL so that you could plug in, you know, whatever accelerator? Or what would be the challenges for you in trying to achieve something like that?
Well, so yeah, it's a good. I haven't really thought about the open sourcing of the programmable logic. So, of course, the programmable logic side tends to be a very different kind of environment when it comes to open source stuff. So, you know, today, yeah, I mean, Xilinx, you know, a large part of your revenue comes from IP licensing and so on of programmable logic blocks. So, we haven't started work on actually terminating the back end request queues actually in programmable logic, but we're working a lot on, you know, packet processing and obviously the integration of virtualized storage and networking in the programmable logic itself. So it's not really that big a stretch to assume actually if you've got a more tightly integrated processor, you could actually get, you know, much better performance if you integrate that as well. I think we're open to discussions on that. We have a bunch of guys who, you know, who on our team who do the FPGA programming side. So as of today, we haven't open sourced any of that stuff, but perhaps we could. Yeah.
Any more questions? All right, let's have lunch then. Thank you.
Thanks.